2.5 weeks has happened since the last time we got together, and cobwebs have grown in the brain. So I want to spend the next 30 minutes going over some stuff we did before the break and pushing the thinking a little bit. Okay, so you've got a handout titled, it's coming around in the green folder, Areas of Bounded Regions, Regions Bounded by 2 or more curves. Basically the idea is this. If I gave you 2 graphs, here's f of x, here's g of x, and I wanted that region, the area for that region, what would you do? Have a quick conversation with somebody near you. What do you remember? I'll take anything from anybody about 1 minute. How would you find that area?
Whichever one's on top. These points or? The points on the side. And I thought whatever one's on top is the top. Yeah.
So you would put, right? We still use it. Definitely.
Yeah.
And then those, whatever points you get, whatever points you get.
All right, let's get some hands on this. I'll take anything from anybody. Where would you start?
Minus f of x.
Side conversations are over. What would you do? I'll take anything from anybody. How would you start? Edgar, you get some thoughts there?
Wrong one.
Abraham, sorry. It's been 2.5 weeks.
Find out which ones fall together so that we can subtract.
Okay. So you want to figure out which one's over the other one so you can do some subtraction. Daisy, what were you going to say?
Yeah, I was going to say, well, in this case, it would be g of x minus f of x.
Okay, so g of x minus f of x because g of x is the one that's on top? Okay, great. What else? I'll take anything from anybody. Anything at all. Jennifer? Find both of the intersection points. Gosh, I love that because that's where we're going to start integrating and that's where we're going to end the integrating. Now, because you don't know exactly what equations these are, you're not going to find a number, right? So for now, I'm just going to call them A and B. What else? What else would you do? What else would you do? I know it's been 2.5 weeks. I'm just curious, what's in there already? One. You're going to do an integral. Good. From where to where? From A to B. What are you going to integrate?
G of x minus f.
G minus f or f minus g?
G minus f.
F minus g.
Uh-oh.
G minus
And
f.
the way that you decide, this is the thing that I was beating into you guys before we left in the break. David, what was the thing?
Decided which of the graphs is on top, which is g of x.
Okay, you would look at like which one's on top, but the thing I was asking you guys to do is I'd say like draw one little slice, right? Draw that one little slice, and there were 2 questions that I'm interested in here. For this slice, question number 1 is how wide? Or how thick is it? And this is going to be like we would call it delta x, or sometimes we call it dx. I'll take either one of those. I'd ask how wide, and then the next thing I would ask is how tall? How tall is that slice? Right? It's g of x minus f of x. Now the reason that I care about how wide and how tall is that what I really want is the area for this little slice. And how do I find the area for this rectangular slice? How do I find the area of a rectangle? Right? It's going to be height times width or length times width. So that's why we have g of x minus f of x times dx. That's the area for one little slice. But what I really want is the area for all the slices. When I add up all these little slices, well, how do I add up all these areas? That's what this definite integral is. So it's an integral from A to B, g of x minus f of x dx. Whatever I would get out of this, that's the final answer. All the friends okay? All right, here's what I want to do. I want to put 20 minutes on the clock to get you guys like some time to work on the homework that's due tomorrow. Specifically, I want us to play around with the hardest question that's on there. You're probably going to want to grab some extra paper of your own. I want to look at problem number 6. You've got 5 minutes. You can work with anybody around you. Get as far as you can with number 6, part A. Do not use your calculator. Just go as far as you can. Haven't heard me say it lately. I think a good picture is worth 1,000 words. Because the cobwebs have grown, I picked friendly function. Mariah, can you tell me about the graphs of the two functions? Y equals 4x plus 3 and y equals x squared plus 3. What do those look like?
X squared plus 3 be a parabola.
Okay, it's going to be a parabola shifted
Up 3.
up 3 spaces. Okay, nice and easy. What about the other one?
It's just a regular, like linear, like the line.
Okay, and what do you know about that line?
It's up 3 as well, so it touches the bottom of the parabola.
Okay. Okay, I kind of drew that one badly, but I hope everybody's okay. We got y equals 4x plus 3. We've got y equals x squared plus 3 in the region that I'm interested in. What's the region? It's in the first quadrant, but what part? What's the part? It's this little piece in here, right? All right, so let's start pulling all the brains together. How am I going to find that area? What do we need? I'll take anything from anybody. What do you need? Marvin?
Points of intersection.
You need points of intersection. Tell me a little bit, how are you going to get those points of intersection?
You know the first one is 0.
Okay, so we know the first one is over here at x equals 0. So that one's pretty nice and easy. How are you going to get the other one? Right, we're going to set both of those guys equal to each other. So if x squared plus 3 equals 4x plus 3, now I just need a little bit of algebra. I can subtract 3 from both sides. I could subtract the 4x. I could factor. And I should have x equals 0 or x equals 4. Is everybody 100% with the intersection points? Nice and easy. Okay, Jose, what else are you going to do? You can turn that off.
Do the from A to Z, so from 0 to 4.
From 0 to 4, those are going to be your limits of integration because we're going from x equals 0, that's your first one, over to x equals 4. Great. Next question, what are you integrating? It goes back to the slice. It's always going to go back to the slice. Noemi, if I asked you to think about one of these little slices, what can you tell me about that slice?
The width is dx.
The width is dx. How tall?
Is it f of x minus g of x?
Now I want to be careful because I heard you say f of x minus g of x, but we're not using f of x and g of x in this problem, right? There's no f of x, there's no g of x. How do you determine the height of this little rectangle?
Top minus bottom.
Top minus bottom. So which one's on top? 4x plus 3. Now I'm going to write it this way. 4x plus 3 minus whole top minus whole bottom. X squared plus 3. My integrand, Daisy, can you tell me what the integrand is going to be? Yeah, the width is dx and the height is whole top minus whole bottom.
What did that equation you wrote there?
Right, it's this guy that I just wrote here. Top minus bottom, but then there's also something else you need.
Oh, dx.
Times the dx. Getting here is probably worth 2 points. I'd probably say 1 point for your limits, 1 point for the integrand, and now all the new stuff is done. I just need old stuff, but it's really old stuff now, so let's finish this off together. What are we going to do next? What are we going to do? Nora, what do you want to do?
Combine like this.
Combine like terms, if you see them, 4x plus 3 minus x squared plus 3. Those guys cancel. So now you've got the integral from 0 to 4 of 4x minus x squared dx. Next thing? Oh, it's been a while. I wouldn't want to factor out. I need the antiderivative. Antiderivative of 4x. Remember, if it's 4x to the first, add 1 to the power, divide by the new power. All those things are in there. We just forget them a little bit. Antiderivative of 4x is going to be 2x squared minus antiderivative here.
Negative 1/3.
1/3 x cubed or x cubed over 3, either way. Integrate from 0 to 4. Finding the antiderivative gets you another point. Now plug in the 4. 2 times 4 squared minus 1/3 of 4 cubed. All that minus 2 times 0 squared minus 1/3 times 0 cubed. Clean it up a little bit. 4 squared is 16 times 2 is 32 minus 1/3 4 cubed. 4 times 4 times 4?
16.
Oh my gosh, 4 times 4 times another 4 would be 64. 0 over there. If I just do a little side work over here, 32 minus 64 thirds. Get a common denominator of thirds. What is that, 96 thirds? Minus 64 thirds. 32 over 3. I'd say that's probably worth another point. Tonight's homework, I want you guys to do problems 1 through 5. If you can do this, 1 through 5 are going to be just fine. Now, part B is the push. Part B, questions like this have been showing up on the AP exam for the last couple of years. These are always the struggle place. So I want to spend the next 10 minutes or so seeing what you guys can figure out with B and C. So B, the line x equals C divides region R into 2 distinct regions. The area of region R to the left of line x equals C is 2/3 the total area of the region. Set up, but do not solve an integral equation, which can be used to determine the value of C. I'm not going to tell you anything Let's have some good conversations with the folks that are around you. Go as far as you can. We'll talk in a little bit. Feel free to talk to the super smarties around you.
Because you know it starts in June. It says first quadrant still.
Did you know it would equal 64 over 9? The integral, right?
Instead of finding from 0 to 1, I just multiply.
Oh, yeah.
So just find 8
I think that makes sense. When you flip them. But when you did look, R plus 0 makes a difference.
That? No. Something like that?
Something like that. I thought you said by equaling it.
You've got the right idea.
C to 4 is 0 to C.
For those of you needing a little bit of a push, I would go back to the diagram. Here's y equals x squared plus 3. Here's y equals 4x plus 3. Badly drawn, I know. X equals c. What's so special about this line x equals c?
Everything
What's so special about x equals c?
it divides the area.
It divides the area into two pieces.
See,
Two equal pieces?
no.
What's so special about the pieces? We know something. I'm not going to tell you. Go back and read the problem again. If you're not sure, go back and read it again. What do you know about where you draw C? Jennifer, what do you know?
The left is 2/3.
The left, this guy here, is 2/3.
2/3 of the whole.
This is 2/3 of the whole area. This guy here is 2/3 of the whole area. So what is that really?
Oh.
If that's 2/3 of the whole area, what's the whole area?
10 and 2/3.
32 over 3, right? If we want to be friendly. This is 2/3 of 32 over 3. How am I going to find this area?
Multiply 32 over 3 times 2 over 3.
I'm integrating, I'm starting over here at x equals 0, badly drawn, right? I'm integrating from 0 up until?
C.
Up until C. What am I integrating? I'm integrating from 0 to C, this little region, which is, what was it, top
Yes.
minus the bottom, and Ron Beer, that's what you guys had over there, right? You said it's the integral from 0 to C of top minus bottom. All that is supposed to be equal to, well, what's it equal to?
2/3 times 4, 10. 32
It's
over 3.
2/3 of the whole area.
See,
and the whole area is
32 over 3.
32 over 3. And if you really read the question carefully, how much more do we have to do?
Nothing.
Nothing else. All they wanted was set it up. Don't solve it, don't integrate it, just give me the setup that you would use. This guy here is going to be the area for this little pink region is equal to 2/3 of the total thing. Done. We're okay? All right. Make me proud, Papa. Go for part C.
Oh, equal. So 1
Oh, shameful.
6 over 30.
Shameful.
You just say multiply this up.
Hey, I want to interrupt all the get thinking process that's happening here. Can you guys show me what a horizontal line looks like? Horizontal line looks like that. Make sure you're drawing and considering a horizontal line. So if you go back to your region, horizontal region. It has to be horizontal. Oh, I will tell you the fact that this is a horizontal line changes everything. I haven't seen anybody moving in the right direction on this yet. It's a horizontal line that changes everything about this problem.
Sometimes you think you're wrong.
Right minus left. Okay, developed this cough in South Texas. Right minus left. You don't have to do vertical slices. We also allow the horizontal slices. We did learn about horizontal slices. And horizontal slices would be better because they are easier in the design. I don't want to do top minus bottom of this line y equals a and all the craziness thing. That's top minus, right minus left. All right, let's pull all the brains together here. Okay, nobody was moving in the direction of horizontal slices. Okay, I can deal with that. But horizontal slices for this one are going to be better. Why? Why would horizontal slices be better for you in terms of your calculations? Look at the region. Look at what we're doing. Why are horizontal slices better here? Adriana, why do you think horizontal slices would be better?
Because it says that there's no horizontal line, which is not equal to A, that divides
region R into two equal areas.
Okay, y equals a is a horizontal line. It is going to divide into two different regions. But if I wanted to do vertical slices, I can handle doing vertical slices. But with vertical slices, I always have to keep in mind top minus bottom. Well, which function's on top?
4x plus 3.
Which one's on the bottom?
X squared plus 3.
The answer is it depends. Are you talking about slices over here? Over here, which one's on top? 4x plus 3 is on top, x squared plus 3 is on the bottom. But a slice over here? Y equals a is what's on top, and y equals x squared plus 3 is what's on the bottom. A slice over here, what's on top? 4x plus 3, and what's on the bottom is y equals a. It gets really confusing in this world of like which one's on top and which one's on the bottom. They keep switching. But if you think about the right minus left kind of rectangles, let's look at that. If I do right minus left, if I'm down here in this first region, which function's on the right?
X squared.
X squared plus 3 is on the right. Which one's on the left?
4x plus 3.
4x plus 3. What about if I'm up here? Same thing. X squared plus 3 is on the right, 4x plus 3 is on the left. What if I'm all the way down here?
It's still the same.
It's still, the x squared plus 3 is the one on the right, the 4x plus 3 is the one on the left. Life would be easier in this problem to be thinking right minus left. Now the problem though is that when you move to this right minus left kind of orientation, a couple of things change in the integral. One really big important thing changes in the integral. If you're doing right minus left, David, what's the thing that changes?
Wasn't it that the values change, so instead of using x's, we use y?
If you're going to do these horizontal slices, if you're going to do right minus left, it's no longer a dx integral. What you need is a dy integral. And if it's a dy integral, what changed? Everything. Your limits of integration change. Your integrand changes. Everything is in terms of y. So let's finish this one off. Where do I start finding the area if I want to look at the area of region 1? Not 0 to a.
3 to a.
I look at the y value. So what's the y value at this lowest point?
0.
Y, right? I wanted to start back with this one because I knew this was hard. Y equals 3 is the lowest value. Where's the highest value? Y equals a is the highest value. I want to do right minus left. Which function's on the right? X squared plus 3. Right, so the right one says y equals x squared plus 3. The left one says y equals 4x plus 3. The problem is if you say right minus left, you're not going to be able to use that in your integram because it has to be in terms of y. So rather than saying y equals x squared plus 3, you're going to have to solve this for x. So solve it for x. Y minus 3 equals x squared. My next move is going to be, we're going to take the square root. So x is the square root of y minus 3 plus or minus. Over here, instead of y equals 4x plus 3, y minus 3 equals 4x. So y minus 3 divided by 4 is equal to x. Because I only want the right half of this parabola, I'm going to use the positive version. So I'm going to say it's the square root of y minus 3 minus the guy on the left, y minus 3 over 4. Right minus left. I'm integrating from y equals 3 to y equals a. It's a dy integral. Life is good. You're not finished. Why not? Why not?
You're missing the other piece.
I'm missing the other piece. That's one reason why I'm not finished. What's so special about y equals a? Jennifer, what's so special?
Don't you have to set all of that equal to 32 over 3 divided by 2? Because it's the same thing.
Right, the place where I draw my horizontal line, this line of y equals a, I'm drawing it so that the area down here is equal to the area up here. So another way to say that, you could say that this area is half of 32 over 3. That's one way to go about doing it. There are other ways. I would definitely put a little star next to B in part C. These are harder than anything you're going to see in the homework tonight. The homework should be an easy, comfortable experience for all the friends in the room. Everybody good? All right, I'm going to turn the AC on because it's getting a little bit warm in here. Friends that are in the back, if I can get all of you guys to move up front, that means you're probably going to want to sit on the floor. Maybe some of you guys want to come sit on the floor. We're going to gather round. I need you to grab the handout called Volume of Revolution Day 0. You might want to grab some colored pens so that you can color. Ron Beer, how do you feel about driving the laptop? You feel okay with driving the laptop? All right, can you erase everything that's over here? And everything that's over there? And Giselle, we're still filming. Folks in the back, move up to the front, please. All right. Go. Good. Is that fine? I caught it. I didn't swat it. Thank you, Christian. All right. No, you guys are going to want to move closer. It's okay. It's okay. I won't bite. All right, we've got about 20 minutes, which is perfect. The homework tonight has nothing to do with this. This next 20 minutes is about taking an idea that we started back in October and going deep with this idea. Way back in the day, our friend Riemann would have said, I want to find the area of this function, the area bounded by this function over here, I'm just going to call it f of x, from some place, x equals a, to some place, x equals b. What did Riemann tell us to do to find that area? What would we do? What did Riemann tell us to do way back in the day?
Methods.
I'll take anything from anybody. What did Riemann tell you to do? Circles? Squares?
Rectangles. Squares already.
Abraham? Trapezoids is one thing that he told us to do. The other thing?
Draw endless rectangles or trapezoids.
Draw endless rectangles, endless trapezoids, right? We had like 4 different methods that we studied back in the day. 4 methods. What were they?
Midpoint.
Midpoint method? Right endpoint method? Left endpoint method? Trapezoids. Now, don't bother drawing this on your diagram, but you know what Riemann would tell us to do. He'd say, make a whole bunch of rectangles, right? How many? A bunch. Okay, really, we're going to get to an infinite number of rectangles, right? You'd say like 1 rectangle, 2 rectangles, 3 rectangles, 4 rectangles, all the way out to this last one, n. And if you wanted the area, this is what I want you to get in your notes. The way that you'd find the area, and I'm going to use the approximate symbol here, have to use approximate here. Why? It's not accurate. I can see from the graph why it's not accurate. Mariah, why is it not accurate?
Because there's like spaces like.
You got like all these little gaps, right? Maybe it's an overestimate, maybe it's an underestimate. But what I would do is I'd say, well, the area is the area of the first one plus the area of the second one plus all the way out to like the area for this nth one. And for each of these rectangles, we would, let's say I'm doing the left endpoint method. I'll call this x sub 1. My partition was like x1, x2, x3, x4, x5, and so on and so on and so on. For each rectangle, I would evaluate the function at the endpoint. I'd say, how tall is the rectangle at this point? I'd find the y value. How tall and then what? How tall and then how wide. And so I'm just going to call this distance here delta x. I'd say it's f of x1 times delta x, plus for the second rectangle, f of x2 times delta x, f of x sub 3 times delta x, and so on and so on. And they all have this same form. The value of the function at a partition point times the width of the rectangle. This is not the thing I'm expecting 100% mastery, just familiarity. We've been here before? Okay, now I can get really fancy, and I would say, well, they all have the same form, so let me use this notation. What was that called again? Sigma notation, right? We're going to go from 1 to, how many rectangles do we have here? N rectangles. They all have the same form. They're all f of x sub I times delta x. But this is still an approximate, because I still have gap. Sometimes overestimate, sometimes underestimate. We're all familiar, right? We've been here before. How do I get the exact area? If I want to get not an approximate, but an exact, how do you get to the exact area? The limit is what happens? Not x. This guy here is n rectangles, like 5 rectangles, 100 rectangles. To get an exact area, you take the limit as n approaches infinity. Because if I'm going to squeeze an infinite number of rectangles into this finite width, they have to get really, really skinny. So I'm going to get this limit as n approaches infinity. I goes from 1 to n, f of x sub I times delta x. That is what Riemann would have told us to do. And I think in our 8 months together, however long it's been, we've actually gone through and done this 2 whole times. Because what do we really do to find area? No one actually does the limit as n approaches infinity of its sum. What do you really do if I say go find this area? Well, wouldn't use the calculator. How would I really find that area? Everybody would do a definite integral of my function times dx from where to where? Oh gosh. From like a to b, from wherever I'm starting to wherever I'm ending. This is what we did back in area, but the way we built it up, we did all those rectangles. We added all the rectangles up. We took an infinite number of rectangles, and that's what gets us over to this definite integral. Done. This is what we did with area. Everything we have done up until today has been flat. Everything has been two-dimensional. Today, yes. Today is the day where your life changes. We're not going two-dimensional anymore.
Don't do it.
It's time to go into 3 dimensions. So we're going to take these flat regions that we've been studying. Well, no, not at the grocery store. I had to go to Party City. Party City. Yeah, I'm investing heavily here. Okay, so we would take this flat region, and we're going to talk about rotating it around an axis of rotation. Your axis of rotation could be horizontal. Jasmine, you okay there? It's only the first day back. Your axis of rotation could be vertical, it could be diagonal, all the things are possible. But we're going to take these flat regions and we're going to spin them so that we can get something 3-dimensional. And in the 3-dimensional world, you don't talk about area anymore. Instead, you talk about volume. Spheres are an example of 3-dimensional. Okay, we're going to talk about volume. Now, the process is the same. And Ranveer, this is where I need you. And you guys just... I am much more interested in the big picture than in your struggling to draw the things. Okay? So we're also going to have some conversation about what things look like. For the same function, from x equals a to someplace x equals b. Imagine taking this region. My axis of rotation, that's going to be this line over here. I would like you to add this into your notes. This is going to be called the axis of rotation. It's also sometimes called the axis of revolution. They mean the same thing to me. The way that you're going to indicate your axis of rotation, you normally do like a little swoop, like a swoopy circular kind of arrow. we're going to take this region here and spin it around the x-axis. The x-axis is your axis of rotation. Take a minute. What will this look like? If you take this region, this shape, and spin it around the x-axis, what do you see? Don't tell me. Tell somebody near you. What do you see?
A ball.
What do you see? Okay, I've heard vase from a whole lot of people. What else are we seeing? You see the vase? I was told the Spanish word for vase last period. What? Not vase. No. Spanish word for vase? That wasn't the word I was taught, so they're lying to me. What? Whatever. Okay, apparently you guys don't know the same Spanish they do. Okay.
What did they say?
I don't know. It was something that began with an H. What? No. Okay. So maybe it's a vase. Some people in the BC class when we did this said it looked like a whale. Did anybody see the whale?
No. I mean, the whale.
How many of you guys see the whale? Or like a goldfish? Like the goldfish cracker maybe?
Yeah.
When I asked Caroline about this, let's see if this sticks. We're going to talk a lot over the next couple of days about what things look like so you can visualize it. I said, if we take this region and we spin it around the x-axis, what do you see? And what she said was Cinderella's dress.
She is amazing.
Cinderella does have some curves. Let's just ignore them. That's what I do. Imagine Cinderella laying down. Right? Not like that. Cinderella, like the big ball gown. Right, the way that it like puffs out. And of course, because she's a Disney princess, she's shaped like no woman actually could be shaped.
Yeah.
Right, she's got like the big poofy dress part and like the really narrow waist. And then something happens up there, I don't know. Right, but it's like her ball gown. Okay, Ramdir, here's what I need you to do. I want to take that one little slice in red. Picture spinning that around the x-axis. What does that one little rectangle look like? Okay, what I want you to do, Ramdir, revolve one rectangle. Just the rectangle.
Whoa.
Not a circle. Not a circle.
Pac-Man.
A 3D circle, which we would call a
It's a wheel.
wheel, also called a sphere. All these soccer players, and you're going to tell me that this is a sphere? It's a cylinder. One rectangle spun around the x-axis. Stay with me. Are we okay with cylinder?
Yes.
Okay. Well, Ramir, show all original rectangles. Right? So imagine Riemann slicing up all these little different rectangles. Still getting some error in this. See all discs and washers. Option 6. Each one of those rectangles gets spun around the x-axis. Each one of those rectangles causes a cylinder to be formed. Big picture, we're okay? The idea is going to be the same. Just like Riemann said to find area, look at one little rectangle and add them all up. What we're going to do is we're going to go over on the side, and I want you to get this in your notes. I want to look at a cylinder. So Ranbir, if you could hit reset, and then revolve one rectangle. I want to figure out not the area for a cylinder, because an area for a cylinder is not of interest. It also doesn't make any sense. But if we're going to talk about cylinder, we're going to talk about volume. So what I need is we need to get clever and find the volume of a cylinder. Who remembers volume of a cylinder? One person? Volume of a cylinder. David, maybe? Volume of a cylinder. Volume of a cylinder, here's the hint. It's a circle that has some thickness. Romby, what you got for me?
Pi r squared times the height.
Okay, some people last period remembered that volumes for like cylinders and prisms is big B times H, where big B stands for the base. What's the area for the base of a cylinder? Area.
Pi r.
Pi, not 2. Area of the area of the base, the area of a circle, right?
Yeah.
So it's, as Rombier said, pi r squared times the height.
But then you have 2 circles, top and bottom.
Volume. I think you're thinking surface area, like you're painting all the things. The way you find volume is, and I'm going to redraw this in a different orientation. So imagine my rectangle is getting spun this way, and it's got a little bit of thickness. I drew that really poorly. Hopefully your skills are better than mine. I want the volume. That's going to be my radius, and I need the height. When I take my one little rectangle, the way that I find the radius, it's actually the value of the function. It's like f of x. How thick is it?
That's
That's the
delta
width
x.
of the rectangle. That's what I'm calling this delta x or the dx. So my volume for a cylinder, don't tell me it's pi r squared h, tell me what the radius really is. F of x squared, tell me what h really is.
Delta x.
Times delta x or dx, depending on how you want to describe it, that's fine to me. So, let's see if I can get this over here. So volume, what I'm going to do is I'm going to say, well, the volume is approximately the volume of the first cylinder, plus the volume of the second, plus the volume of the third, all the way out to the volume of the nth, whatever one. Right? All those little rectangles that Rombier showed us before, spin each one of those. Well, each one has the same form. It's going to be pi times your radius. It's f of x1 squared times delta x. Plus your second one, pi times f of x2 squared delta x. Plus all the way out to the last one, pi times f of x sub n squared delta x. They all have the same form. That's a good thing. Because they all have the same form, guess what? You can say that your volume, rather than writing them all out, let's use sigma notation again. And so we're going to go from 1 to n, pi times f of x sub I squared times delta x. That's how you're going to approximate the volume if you want to look at like n cylinders. Big picture, is everybody mostly okay? It's the exact same idea with area. Apply it with volume. But this is going to give me the approximate volume. You guys know the answer to this next one. How do you move from the approximate volume to the actual exact volume? You're going to take the limit, because what you want is more cylinders, more slices. So the way that you get your volume, your true volume, is you're going to say it's the limit as n approaches infinity of this sum, I goes from 1 to n, pi times f of x sub I squared times delta x. We got about 1 minute left, just enough time. This is going to look like magic just happens. And that's really what happens. If we're taking the limit as n approaches infinity of this infinite sum, rather than doing an infinite sum, we're going to do an integral. That's exactly what happened over here with the area, right? This limit as n approaches infinity from 1 to n became your definite integral. Same thing happens over here. Limit as n approaches infinity from 1 to n, that's my integral. What's my function? It's pi f of x squared dx. Pi, function squared, dx. The only thing that's missing are the endpoints. What are the endpoints? It just depends on where you start and where you end. So I'm going to call that A to B. One last thing. that is a formula, but if you look it up in a calculus textbook, that's usually not the way they're going to present it. They're going to do something with the integral. There's some legal thing that you can do.
You can take the pi out.
I can take out the pi because
It's
pi is a constant. So the thing that is most likely going to happen, you're going to see pi, definite integral from a to b, f of x the whole thing squared dx. That's how we're going to find our volume. Tomorrow, we're just going to play around with this. This is like the new tool in the toolbox. So just a reminder, where are we meeting tomorrow?
35.
Room 35. Homework tonight?
1 through 5.
1 through 5. Favorite calculus teacher of all time?
Mr. D.
No one said something ultra good. Okay. See y'all later.